All right, we got session 14, and we're going to continue where we left off on 13, talking about element-wise operations.
Yes. So, and as we do that, I will also talk about the changes that have occurred since we talked about 32-bit, 64-bit integers. So every matrix now has up to 3 different integers in it. And I'll show you how I handle that. And there's a new folder, some new stuff around as well, some new codes. Okay, but let's go to add, and I'll just do this naturally as we come along the code. So this is now we're into the element-wise add. It's doing a set union of 2 matrices or vectors of the same size. And then there's 2 variants of this. There's one in the spec and there's one extension. There's the EY's add, which I don't have my camera turned on, but I'll just explain it. You have an operator, a binary operator. It can be an index binary operator now, where the operator is applied on the intersection of the patterns of A and B, A plus B. If you're in A but not B, or B but not A, you just fall through to the output. So Cij is just the typecast of Aij, avoiding the operator. That's kind of awkward, actually. I wish that wasn't the default, because some cases, like if the operator is less than, what does it mean to typecast A to C? That doesn't have much meaning. So I have a variant called EY's union, which when you're in A but not B, the value of Cij is the operator is always applied. And in that case, the operator is Aij, applied to Aij is the input for A, and B is a scalar called beta, which is like a placeholder. Anytime Bij is not present, beta gets stuck into the operator, and beta is an input parameter to the method. So
And
those two,
I assume you can emulate add by just using the identity, right? You can have a 0. You can essentially stick in a 0 equivalent, and you get depending on the operator.
but operators don't always have an identity element.
Yeah, okay.
0.
Right.
Like an index binary op produces an integer with indices. Well, there's no identity for that.
Okay, gotcha. Yeah.
So there's no way of fusing them into one method. They're just tweaks of the same algorithms. There's a few places where I'll branch to one versus the other, how you're doing it. But it does affect some other things like typecasting. The typecast for EY's multiply and EY union are the same in that the output of the operator must be castable to the matrix C. That's it. And that's a lot simpler. For EY's add, not only that must happen, but it also must be that A must be castable to C and B must be castable to C. That's really awkward if you're trying to create an EY's operator, element-wise operator that says compares 2 user-defined types and produces a Boolean, and you want a Boolean output. Well, then how do you cast a user-defined type to Boolean? You can't. It will fail. There's no way to do that. So EY's union is more flexible, but there's no way of like having one method that somehow does both. It's one algorithm. All my kernels are the same. They just specialize depending on which variant you're doing. Are you an EY's union or EY's add? Do one or the other. So you'll see. Otherwise, the algorithms are very, very similar. In fact, if you look at the top level GRB matrix EY's add, I'll pull this up and compare that with GXB matrix EY's add. So here's EY's add. There's several variants, one using the multiplicative operator of the subring, one using the monoid additive entry, but those are really trivial. They both call directly EY's, GB EY's, and they just pass in a Boolean to say this is EY's add and it's not EY's union. But both of these methods eventually come back after called EY's, which I think I showed you this level already. So the first step in the EY's add is actually go to the EY's folder to call EY's, which does both EY's mult, EY's add, and also EY's union, the 3. And then that method, EYs, calls the method in the add folder, which is gbadd.c. But this method can do, let's see. This method has a bool that says, are you EYs union or are you EYs add? And if you're EYs union, you've got the scalars alpha and beta. So I'll get to these. This is the core working method right here. So EYs add and EYs union are essentially the same, except that EYs union just passes in those alpha and betas and passes in the scalar that says use them, please. So this is, so let me pull this up on the right side here. This is EYs add. So it's now not working on the user's matrix C. This is a temporary matrix that's being constructed and will be added in later. I think, yeah. I think the EY's case has already handled some of those other cases. So there's properties of the matrix, output matrix I have yet that I pass in separately then as a result. But otherwise, it's got the same inputs as the original algorithm, the top level user's algorithm, but I've pulled out the descriptor. This is a parameter. Do I apply the mask? So in many of my algorithms, I try to use the mask as best I can to reduce work, reduce time, reduce memory. Sometimes I'll finish the work entirely in the method itself, and then I can skip the following accumulate mask phase, where you take the output, pump it through the mask and accumulator phase. I can say, hey, I've done everything. I don't think this will do it here, but this method does decide if the math is able to be efficiently exploited during the EYs add or not. Okay. And if it's not, it'll be applied later. And if it is used, well, I may have to use it later anyway, but at least I've saved some space and some time by using the mask as we go. But there's some cases where, especially when the mask is complemented and sparse, it's hard to use the mask. It can be slow. So I'll just do the add, compute a temporary result, and then I'll throw away entries I don't need later. That's what this mask applied thing is. And then I've got the two input matrices. Then I have the bool to tell me which kind of add am I doing. It's always doing the set union, both methods. That's why this method is one method. But what do I do if it's an A but not B? Do I typecast from A to C, or do I pull in the operator and pass in beta? And if so, alpha, given alpha and beta, there's the operator. And then there's this flip thing. Depending on how I call this method, sometimes I'll make changes like, oh, I have a matrix stored by column, stored by row, and I unify those into one method. But when I do that, if the operator is say plus, it doesn't matter if it's A plus B or B plus A, I get the same result, whether it's two things this way or this way. I can flip things around I may reverse the two matrices to reduce the number of kernels I have to write. Okay. And well, if I do that though, there's cases where I may have to change the operator, like less than becomes greater than. But there's some operators that can't be reversed with a different operator. I have to take the existing operator, but I may have to tell it, well, the row and column indices need to be reversed. So that's what flip INJ means. That means where you see a row index, put the column, where you see a column, put the row. Because I'm working on maybe the transpose instead. Or maybe I've transposed the matrix, and so I need to undo the transpose to give you the right index computation. So this just means reverse the roles of INJ inside an indexed operator. This is an interesting flag here, A and B disjoint. This is a very special case, but it speeds up my code a little bit. Sometimes I know by construction that the two matrices I'm adding have no entries in common at all, in which case there's no operator to apply on the set intersection because there is no intersection. The time I know when that will happen is in wait. See, GB add is a method that's used in a lot of places for a lot of things. It's used as the EY's add, EY's union, but the element-wise add is also used as the accumulator step. So if you look at the accumulator mask page, you'll see a call to EY's add, this GB add function. It's also used in one other place. It's used in the pending summation of pending tuples. So as I'm building my matrix, some methods, particularly assign, but then also a few others, can use assign as their accumulative mask stage. In fact, all methods can do this. So assign, I can, if I have a tiny assign, like assign 3 entries into the matrix, they're new entries, they don't appear. Oh, where do I put them? Well, it's too expensive to stick them in now, put them in later. So they go in a pile that grows of pending updates. Well, because they couldn't be inserted, that means they're disjoint with the current matrix. So all pending tuples are disjoint in pattern with the original matrix that they're being input into or pending updates into. So when you do GB wait, which either happens by the user asking me to wait on the matrix or by me by saying, hey, this algorithm can't tolerate pending tuples, add them in. Well, there what I do is I take the matrix, I take my pending tuples. The pending tuples are just a row, column value in order. I use build to build that into a matrix, and then I add them together. But when I do that, I know they're disjoint by definition. So this flag then I can exploit to speed up a few cases. But this is basically what EY's add does. But these comments are a little bit old because EY's union can do more than this. So in fact, these rules here, I should probably revise this for EY's union. The above is revised to the following. So here, this changes. Cij becomes the operator applied to A and beta. And this becomes, so it always goes through the operator. And instead of Aij, I stick in alpha. There we go, alpha and beta. And there's beta here. So that's what this method is doing. So the sparsity pattern is the same, but what happens on these places are different. Okay. So, typical debug assertions at the beginning. If assertions are turned on, I'll check all my inputs. And I think I described my debug scaffolding approach. But let me just mention that here. If you ever think, oh, you're like working on a piece of code and hey, I'm developing it, you just stick here, define GB debug at the top. Okay, and then you go down. Now all these assertions become active just for this file. If you want to do it GraphBLAS wide, it gets pretty slow, but you go to a different file. There's an include file called gbdev.h. Change it there, it changes for everybody. But if you want to do it per file, which makes sense because otherwise it gets really slow. And when this happens, all these asserts turn on. And these things with this GB0, these are things that are printing the matrix, potentially. 0 means don't print, just check. But if you have a bug here, if I have a bug here, what I'll do is I'll say, well, I want to print level 2, which means print the first 30 entries. And that'll print all kinds of things about the matrix. And I can look at the output matrix, and the output matrix is maybe garbled. Garbage, and it'll tell me why it's bad down below. So output for add, this assertion might fail. So I'll turn on the print and I'll print out and it'll say, hey, the row index is out of range. Oh, what happened? Something broke in the matrix.
Does that use the printf function support? Like if I pass in a
yes.
printf? Okay, cool. Because
I
just
you
support
always
it.
use.
Yeah, I just got that working for Postgres, so now you can turn on burbling and it shows up in the client.
It's the same
pretty slick.
printf. Yeah. Any. So what this assert matrix OK is doing, I could show you that really quick here. Act define assert. Where is this? Here we go. It's different, by the way, it's different. The macro depends on, are you in a JIT kernel, in which case it's just turned off. It's too much to print from the JIT kernel. Or are you in the primary library? If you're in the primary library, the matrix OK function, if you have, first of all, they're empty, and they're all empty. But if, no, they're empty if debug is, let's see what happens. Oh, assert OK. I see it's assert OK. Yeah, so if debugging is disabled, they just, all these things evaporate. But if assert OK checks the method and it asserts that the output must be GRB success, and the checker is my print method. So if you look for matrix OK here, assert matrix OK calls my matrix check function, which is my print function for the matrix. It's my pretty print. The pretty print for the function is not just the print, it's also a checker. And you can tell it to print nothing, and then it'll just check. And it'll return success or invalid object or invalid index or something like that if there's a failure. So you can check without printing, and that's by default level 0 here on the printing. Okay, now this is slightly new. All of my integer arrays, CP and CH, are now void stars, because now it can be arbitrary integers. And this will tell me, this will be set to decide, hey, are you 32-bit or 64-bit? These 3 Booleans. Okay, EY's add can't tolerate any pending work. So GB matrix wait says finish everything. And this is a per algorithm basis, right? Some algorithms would tolerate jumbledness, row indices, like if it's stored by column, row indices out of order. Some algorithms like the matrix multiply, they say, fine, I don't care. They take inputs that jumbled, they produce outputs that jumbled, no big deal. I treat that as pending work to be done later. There are some algorithms that can't tolerate that. If I need to do a binary search on the vector, right, they have to be sorted. Okay. So that's what the wait's there for, CD add. So the next thing I want to do is many of my methods, let me go one step up. If you look for a method with the last bit of the name called sparsity, all these different methods are making a selection on, oh, no, except the JIT method, that's different. These various methods, the mask, the MXM, the EYZ, the emult, assigned as its own thing. It doesn't have this, I guess, because it doesn't change the sparsity of the input matrix C. But these things are deciding, let me look at this file. This method is deciding the sparsity format of the output matrix C. So I've got, and it's deciding, is it worth it to apply the mask or not? Can I apply the mask for this operation? So I pass in the mask and its descriptor and the 2 input matrices. And so this is, and there's then a whole ton, and I've got these all different cases, all, because I have 4 matrices and I have 4 formats. That's 4 to the 4 different combinations. And in all of those combinations, I have a decision to make how to make the output. So how to build the output. And that'll determine which algorithm I'm going to use as well sometimes. Although right here I see, I think with the EY's add, I'm just passing this in. Although in this case, the add phase 0 may change it because it's an input output. It may make a different decision.
And it looks like the the pattern here is that full beats bitmap, which beats sparse, in a sense.
In this structure here, yeah, like if you add, say, full plus bitmap, well, because it's a set union, you'll get full. EY's mult will be different. This would be bitmap because it's a set intersection, not a set union.
Got it.
See, so there's different little changes like that for all these different methods. And this is when there's no mask. When there's a mask, so this is the decision here. When there is a mask, well, it depends on, well, is it complemented? Is it sparse or hypersparse? So this is not complemented. The mask is sparse. Oh, well, then the output's going to be sparse.
Always sparse. Yeah,
Yeah.
I see. Yeah, which makes sense if the
If-
mask is sparse and it's not complemented, the result is going to
exactly.
carry that
Yeah.
over. Yeah.
And I do exploit lots of special cases, and here's some of them. M is A. Like, are you asking me to do C of A equals A plus B? Okay, that's a very special case, I realize. And there's this easy mask condition I'm computing here. There's various, a lot of algorithms are like this, they have special cases they exploit. And this is one of a few of them. And here I'm deciding, do I want to apply the mask or not? And here there's a macro, I could have made it a static inline function. It's a pretty short little function. I apply the mask in this case, only if the mask is very sparse compared to A or B. Because this case right here is fairly difficult to do because I'm doing both a set union on A and B and then a set intersection with the mask at the same time. And that's kind of costly. And it's only really worth doing if the mask is extremely sparse. Otherwise, just add A and B together, get a temporary matrix, and then pump it through the mask. So that's this easy mask thing, or the mask very sparse condition. The algorithms will work either way, but there's a trade-off in performance. And then I may make some changes to this decision based upon whether or not I'm, basically decide this is the same decision up above that I pretend now there's no mask. Otherwise, oh, the output is sparse. And then I have the case where the mask is present, but bitmap not complemented bitmap at full, and so on. The conditions go on. Okay. And I have to handle, it's a very short, it's a very short file, this decision, but there's a lot of cases it has to continue. So I have all these little tables that help me remember what it was I did to make these decisions. So this is the sparsity. So now I've got a sparsity here that's, sparsity of decision for C that's either sparse, hypersparse, bitmap, or full. And I decided at this point whether or not to apply the mask. And I think that's the final decision for the apply mask. Yes, it is. I don't change it later on. No. Okay. Now, a lot of my algorithms are multi-phase. And this is a three-phase algorithm. Phase 0 is going to finalize the sparsity decision and also find what vectors will appear in C. It's a set union of the vectors of A and B, basically. And so I want to find that set union of the vectors to compute of the output, and also a mapping of which vector in C, because it could be two, I could be doing a set union. If they're all sparse, if they'll all say CSR, CSC, well, then it's easy. It's just everything. Every vector in A appears, every vector in B appears, every vector in C appears. But if they're hypersparse, I have to do a set union on the vectors that are present in A and B and take their union. That gives me the vectors to compute for C. And then I also want to construct a set of mappings to say, this is the third output vector C. That corresponds to the first vector in A and the second in B. Right? And that mapping is not the same as it's not the first column, and it's got to be the same column in the matrix. But it's which is it the first or second or third that appears in the data structure, that's different. So I have to create a mapping of who is connected, which vector is connected to which. And that's what these mappings here are. I also have to connect, like it could be the 10th vector of C is the same, maybe it's column 100. Okay, column 100 is the 10th vector of C, it's the 5th vector of M, the 17th vector of A, and the 42nd vector of B. Okay, so I have all these mappings that I have to keep track of, and that's what phase 0 is computing. And phase 0 also decides how to build the integers of the output. How do I use 32-bit or 64-bit? And then I burble to tell you what I'm doing. I might say, no, I don't like the mask, I'm doing it later. And I burble here the sparsity pattern of the output, the sparsity of the 3 inputs. Okay. Now, the phases are going to differ based upon whether I'm doing bitmap or full, or sparse or hypersparse. Okay. Sparse is harder. This is just the big overview. I have to first decide what parallelism I'm going to do, and then do the work. And all of this does the analysis phase to decide. It's like a dry run. A lot of algorithms are like this. They'll do a dry run. They won't compute the output matrix, but they'll compute the size of it and the amount of pieces that every thread will see. Like this thread has 107 entries in these 4.5 columns or something. And so that thread or task, which I'll probably usually have more tasks than threads. So I get load balancing because these tasks are I try to balance them, but they're not perfect. They'll take different amounts of time just because of the nature of the irregular computations. I balance what I think the work is, but then the time it takes to do that work can vary. Whenever I say task, by the way, I don't mean an OpenMP task. I mean, essentially, it's my own tasking. I'm just gonna have a parallel for loop that's gonna iterate over the tasks, do so in parallel. Each iteration is another task. That's all. It's that simple. And so I'll split up the work. And so this is doing the analysis phase of the ad. First to split the output and then to do the counting. And then, and I break this up into 2 algorithms because there's other places where these kinds of analyses are really useful. Like EY's slice. Let me see where else this is used. EY's slice. I write my code so it's easily greppable in this sense. I think I've mentioned this before. Where do I use a method? Okay, name of method, space, left bracket, or parentheses. Always. Okay, if someone contributes code that does this, I say, no, that's bad code. You will not find that because then I have to hunt. Like, where do I call this stupid thing? No, there has to be one space before the parenthesis. Don't edit the code and submit code with no space. I know that's a stylistic kind of oddity of me. I was once typing in MATLAB and I was at the command line and Cleve Moeller was over my shoulder. And I wrote something like, it was pretty funny. I was inside MATLAB and I wrote, oh, let's see, abs of, -3. This is Tim. He's got a kind of gruff voice. What are you doing? What is that space doing? He got a chuckle out of that. He thought, whoops, sorry, I wiped out my screen.
That was excellent, Cleve, by the way. That's exactly how he sounds.
Yeah. Tim, what is that? What are you doing?
Yeah, you should
I
do
can't.
that.
Yeah. So you know him, yeah. It was funny. So even here, look at that. Even when I have to go multiple lines, look where I put the parenthesis. Just stylistically, so I can search for this thing. All right. So where do I use this? Lots of places. EY's add, in the assign even. EY's multiply, and also in the masker, which is not doing an EY. The accumulated masks phase has an EY's add called in it as well, but it also has a mask in it, a mask phase where I have to pump a matrix through the mask to the output. The parallelism of that the analysis phase of that is exactly the same as EY's add, EY. So I call it EY slice. So I'm going to slice up the matrix into pieces. So I do that. And so I don't know, I call this phase 1A, EY slice, phase 1 counting. Bitmap of full is either easier or easy. I just have to decide how many threads I'm going to use. And then I do the actual work. And then this may branch into multiple methods as well. This will branch into the bitmap case and the sparse and hypersparse case. And quite frequently, the full case is just a special case of sparse and hypersparse. Because if you think about a matrix that's full, it's just like a CSR matrix, say, except the integers are not there, but they're implicit. But the storage of a full matrix, all entries present as a bunch of values, is identical to a CSR matrix with all entries present. The numerical values look just the same. Because I don't allow gaps. There's no, like in BLAS dgem, there's a leading dimension, and you can say just here's my dense matrix, but it's the leading dimension is different. I don't have that, unfortunately, for my full matrices, which would be handy to have, but I don't support that. So sometimes I don't have special cases for full, except at the very, very end, where I say, "Whoa, what's the integer? Oh, it's trivial. Just compute it on the fly. Don't look it up." And that's my full matrix handling. Sometimes I'll have special methods just for the full case, like sparse plus full. I may have a kernel just for that. Sometimes I don't. Sometimes I specialize down later, deeper in the kernel, so I have less code to write. And then if performance issues come up, I can visit that later. So EY slice is used in a lot of places. And then that's it. That's the total work. But then what are these? So this EY's add, just stitching together high-level methods together. So let's look at each of these pieces in turn. Phase 0. Okay. This whole folder is 4,000 lines of code, right? This is a EY's add. It's a big beast. EY's multiply is about as big. Phase 0. Okay. So I'm doing this, and this is the, yeah. Okay, so I'm not EY slice yet. I'm just deciding the sparsity and finding the vectors. This is a very fast phase. It's not looking at the entire matrix. It's just deciding the mappings, and it's computing the hyperlist of a hypersparse matrix C, if it's hypersparse, if the output is hypersparse. If it's not hypersparse, this becomes super simple over here. Okay. So what does this do? This, by the way, the prototype is not here. It's a macro. The reason it's a macro is that there are JIT kernels that want to call this method, because this analysis is useful in other places. I forget which ones at the top of my head. I could look. Probably assign, I think, the assign methods. The JIT kernels want to call this method. So it's a callback. It's a method that the JIT kernels call. So this function pointer is inside a list struct of about 15 or so different function pointers that I pass to every JIT kernel, so they can be called from the JIT kernel. Because JIT kernels want, I don't link, when I load my JIT kernels, I don't link them against libgraphblas.so. Because then which libgraphblas.so am I talking about? Well, this one. Well, how do I find myself? How does a library find itself? There's no easy way to do that I know of, especially that's portable across platforms. So I don't link a JIT kernel. There's no link dependencies from a JIT kernel back into GraphBLAS. Instead, I pass in function pointers to methods like this. And they're only called a few times, so it's fast. Okay, again, usual stuff. Check inputs. This is always just a pile. This is a very stylistic way of working on these codes, but it's super helpful to me, as I'll sometimes assert here that the matrix is sparse or hypersparse and not bitmap, not full. That tells me a lot later on that, oh, I don't have to handle that condition. It'll tell me here, for instance, the mass matrix at this point may actually be jumbled because it's not going to care about the row indices of a CSC matrix. But wait, Tim, you just did a wait on here. Well, yeah, the other methods might not. They might call this method with a jumbled matrix. This is telling me that it's okay to have a jumbled matrix. Now, this macro jumbled okay is actually, it's asserting that the matrix is either jumbled or not jumbled. Well, that's actually in the data structure, it's just a Boolean. It's just checking, is asserting that the Boolean must either be true or be false. Well, that's obviously a tautology. It's actually doing nothing at all. But I'm asserting that it should do nothing. Because it's visually telling me that, oh yeah, this is a jumble tolerant algorithm for that matrix. It's not tolerant about zombies. I cannot tolerate zombies. I probably could, because I probably don't even read the indices. Okay. But I don't have to. And it's also not tolerant of any pending operators either, pending inserts, pending tuples. So this is for me very useful to do. I consider this kind of code really an integral part of the algorithm, to assert all my inputs, do the work, assert my outputs are okay. All right. Well, if you're calling this and your output matrix is bitmap full, there's nothing to do. I return quickly, which then this falls out and does nothing. Otherwise, I have some work to do, and I have some work to do in particular on this matrix CH. Now, this looks kind of weird, but this is a declaration of a set of pointers that are either this is dealing with 32-bit, 64-bit. So this is a good place to do this segue really quick. I have a file called gbopaque.h, and I put actually a link to it from my home directory because I get to it so often these days. It's actually inside like source built-in include. So if I go to built-in, no, where am I? / built-in include gbopaque.h. There, that's where it is. I have these declarations. All right. Getting the content of a vector, scalar, or matrix. You're seeing it here, so I'll show you how I do it here. Oh, sorry, this is out of date. 3 types of integers. Oh, this is out of date here. Yeah, 3 types. 1, 2, 3. Okay. Well, matrix data structure, which I've already described to you, has up to has all these different integers. There's the offset array, or the point. I call it the P array. P for pointer. It's not a pointer. It's an integer. And there's a Boolean flag now that says true or false. Are you 32-bit? And if it's false, you're 64-bit. Now, once I go to the future, right, internally, that'll change to a number or something other than just true or false. But right now, it's just true or false. And the row indices of a CSC or the column indices of a CSR are the indices, I array. They can, again, also be 32 or 64. And most of the time, so it's just a void pointer. The integer array, if I know there's not zombies, I usually declare it uint32. So I'll load in an integer and it'll just be uint32. But if I know there could be zombies present, I'll cast it to an int32. So a negative number is a zombie. And then the J, this is I for row and J for column. This reflects my column-oriented mindset. Every matrix is stored by column. Well, they're not, but I pretend they are. So I is a row index. J is a column index. Of course, it's not necessarily a row or column, but that's a dyslexic issue to handle later. So that's the name of the array inside the matrix. And then I have the hyperlist as well. But see, the hyperlist has a column index in it. Well, row index if it's CSR. has a column index. So that's the J is 32, J. And so if you have too many columns, that has to be 64-bit. If there's fewer columns, that can be 32-bit. But the hyperhash is all, I didn't think I described the hyperhash already, didn't I? This is a sparse matrix that has the hyperhash is a hashing of this list. It's the inverse of the H array, basically.
Yeah, we covered that in the beginning.
Yeah. So its integers are all the same and they match the hyperlist. So that gives you 3 integers. P controls the P array, I controls the I array, and then J controls all of this. Okay. Now, to get to these 2 kinds of integers, how am I going to do this? Like I thought about, gosh, I've potentially, 1,000, if I have a matrix, I've now 8 variants, 3 decisions per matrix. That's 2 to the 3 is 8. Something like EY's add, there could be 4 matrices. That's 8 to the, no, that's 4 to the 8. Wait, what is this? 4, no, it's 8 times 8 times 8 times 8, 8 to the 4 different combinations. Do I really want to write that many kernels? No, that's 4,096, right? I decided what I could do is do it on a very late basis. Most of my algorithms push the decision, are you 32-bit, 64-bit, down to the very fine-grained step. I'll show you how I do that. What I do is I do this differently, though, if it's a JIT kernel than if it's a factory kernel or if it's a like inline just primary code that's not compiled at runtime. And so this method here, this little macro says I'm declaring a pointer. Well, it's actually 3 pointers. One is a void pointer, and the other 2 are either a unsigned, you can pass in U, or a blank. If you pass in blank, you get signed integer. If I pass in a U, I get unsigned integer. And I get this is declaring 3 pointers, CH, CH32, and CH64. CH is a void. And that's useful because if I try to access CH and index into it, well, the compiler will say you can't do that because, well, yeah, that's correct because I don't know the type. CH32 will be cast to uint32. CH64 is cast to uint or int 64. And that I can index into. How do I know which one to index into? Well, it's with this macro. Basically, what I do is if I have an array like CH and I want to get a pointer to its content and assign that to the 32-bit or the 64-bit side, well, that's what this does. It assigns, like if it's 32-bit, the CH, the array 32 gets the pointer, or if it's 64-bit, it gets the pointer, and the other one's null. So I have a null for one and a valid pointer for the other that's now typed. This is templating in C, right? This is, okay, sorry. Then how do I access this content? Well, I think if I have an example, yeah, here's an example. So here's how, what is this doing, right? This is basically doing the following statement. This is this is the equivalent of saying J equals CH of K. This line right here. But what it's doing is actually, since this is not inside a JIT kernel, what I'm actually doing is this macro right here. This means get an integer, get an entry from an integer array. It could be 32-bit or 64-bit. So what it's doing is say, well, and you notice the concatenation symbols here, so I can use this for any kind of array. So I have the name of the array concatenated with 32, or the name of the array concatenated with 64. And I just look at the pointer, pick whichever is not null. So it's the last minute decision to grab the 32-bit or the 64-bit integer. And then for convenience, I just cast it to 64. That works just fine. If it's 32-bit, it's instantly 64-bit as a scalar. And I have a similar macro for the opposite, which is the set. this sets this either if 64, I'm not sure why I made the decision here if 64, but whatever. If the 64-bit pointer is non-null, assign to it, otherwise assign to the 32-bit pointer. And I have a case where I went to increment. This is basically doing, and inside a JIT macro, these three basic macros change. Inside a JIT macro, they just look like this. Just look up the array because it is one type. Assign into the array because there's just one type. Increment, that's just what they're doing inside a JIT kernel. So the JIT kernels, those branches are compiled away. They don't appear. They're not even compiled away. The compiler doesn't even see them. So this is my framework for, and there's more to this, but this is the first level framework for setting up these 32 versus 64-bit decisions. Okay. So that's what these declarations are now all doing. But now this workspace array is just going to be just in 64. Now, if I was more clever, this is, I could decide, oh, well, actually, some of these could also be type polymorphic to a 32-bit, and I just haven't done that yet. In some places, my workspaces are specific, 32-bit versus 64-bit, but this is a very small workspace. It's just proportional to the number of vectors present in the matrix. So I've just left it 64-bit. If I decide this is a performance bottleneck, I want to save some space, I could declare these as either 32 or 64 and choose between them depending on the, is how big are the three matrices are being played. But I would have a lot of decisions, choices to make of the integer sizes, and I just didn't want to put in all those rules. Okay, I think did I describe my Werk space? The German.
We haven't gone into that yet.
This would be a good place to do that then. This is kind of a bit of a segue, but it's going deep into the Werk. So we will Werk now. We have not been working until now. Now we do the real Werk. Sorry, it's a bad German accent. I named it this way, not because I'm making fun of German work.
Well, it means factory, right?
But, huh?
Werk means factory.
Well, yes.
Yeah.
Well, it means, yeah, it does use for that. It's a more broader word, I think, in German. But anyway.
There's also
So
Arbeit.
Yes, Arbeit is different than Werk.
Yep.
I know, I did study German. So, but I only picked it. I picked it because it's close to the English word work, and it's also a misspelling of the English word work, if you will. And it's then easy to grep in my code. I wanted to have what's work? I want workspace, but I want to look for it and grep for it easily because I use the word work all over the place. So let's make it Werk, and then I can grep for it. Okay, so what is the Werk doing? Basically, what I do is I'm trying to reduce the number of mallocs and frees in my code. And so for small things, like let's look at grb add. You call grb matrix EYZ. The first thing I do, first thing I have to do, and maybe this is a bad example because it's hiding in a macro, because I have 3 versions of it. But I have this little macro to start off with, and this is a macro that's used for every user-facing GRB and GXB method, and it's going to do some basic checks of the inputs, A, B, and the mask and the C matrix. It's going to also log where you are, and it's going to set up the error handling mechanism for GraphBLAS. So every GraphBLAS method may produce an error, and there's this GRB error thing that wants a string. Where do I put the string? This is setting that up. So there's lots of sort of, at the user interface level, I don't do this for all my internal methods, but I do it once, and then I'm going to pass all that thing down. Well, that's in this object called the Werk object. But I put something else in this space. I put in some static space. I can basically, the C alloca ends with an A. Put stuff on the stack, please. And then you don't have to free it. It just goes away when you return. That's kind of like what this space is, but I don't use alloca because alloca is not portable and it might blow your stack out and so forth. So I use my own, it's like my own little alloc with an A. So it's a stack. It's my own little bitty stack. I know this sounds kind of crazy, but it does save time and space to do this. And I have to set up the error logging anyway. So I kind of do this. And so for every method, I have this this setup, and the VARC is telling me, let's see. So there's a whole ton of validity checks. So this is the where for. It's checking 4 arguments and is setting up the where. So I do the following. I decide, let's see, here we go. I decide, where's a good place to start? I'll start, whoops, where is this? Include. Okay, this is a good place to start is the data structure. What is the data structure I'm having here? Well, okay, it's serving at least 3 different purposes. This is my workspace. This is a small amount, 16K bytes of stack space, basically. This is declared statically. This object gets declared statically inside the method as a static array of size. It is static. I guess it's not static. It's what is it? It's on the call return stack, right, of the method. But it's limited in size. It's just 16 kilobytes, tiny little thing. This also is holding for me I set pointers here to say, if there's an error that comes up, here's what you need to do to handle the error. I want to know where I'm calling it from, so I can put that in the error message. And I want to know, where do I put the error? Well, typically that's the component of the output matrix. Well, I pass around temporaries here and temporaries there and workspace matrix here. Where is the output matrix? I don't want to keep track of that. So right as I'm entering any of my user visible GraphBLAS methods, I say, well, the output matrix is right here, and here's its logger, here's its error log. It's set here. And so the logger handle is set to be and when I call the where thing, I set it here. I do this vark init. It sets the string, it sets the logger handle to be null, but then below when I get the matrix, oh, it's the where is it? The logger gets set. If you pass in a valid matrix, I free the error of that method, and I say, here's, if you need to allocate the string, here's where to put it for the error log. Okay, so that's what this is doing. Like I said, it's doing 3 things. It's got the workspace, it's got the error handler, and then it's also got this thing, which is new, which is the integer control. This is a combination now of multiple things. The output matrix you're computing, the C matrix, typically of most methods, it's called, may have some requests to say, I would like to be 32-bit, please, or I would like to be 64-bit, please, or by default it's 0, which says look at the global. Okay, so what is the output matrix? Well, again, I may lose track of that, and I don't want to pass it around all places because I may be working on temporary matrices all over the place. So I fused together. I take that input matrix that has those controls on it, and I combine it with the global setting. And this just tells me then for this method, if I want to produce a matrix, here's how to control the integers. And the P or J or I control is either 32 or 64 for this at this moment. If it's 0, it's going to be chosen as the global control, which is 32 or 64. So this is based, each of these numbers, each of these uint8s are 32 or 64 right now, I think. Yeah. So so that's what the vark is doing. And then the workspace, the 16 bytes, it's really handy to have here, for instance, because what's going to happen for this, for a lot of my parallel algorithms, are going to need some small amount of workspace per task. A byte, or a word or 2 words, like start, finish, or other things. The small, like an array of size, the number of threads, or array of size, the number of tasks of int 64s or something like that. It's tiny. It's not going to be anywhere near 16 kilobytes. So I could just malloc this thing. Well, but then there's more mallocs and frees going along. And codes like Julia don't like to see lots of mallocs. They like to see as few mallocs as possible. So I reduced this by putting this little tiny space. And then what I can do is I have these methods. The prototypes are push callback methods. So this is just comments. But basically, I have these workspace declare functions, which here, this is what we're seeing. It's declaring this pointer of a given type, and it's also declaring a few other helper integers or bools or variables that say it's on the stack or not. Because if it doesn't fit, I have to malloc it anyway. And how big is it, and how big has it been allocated? And so I can basically do push and pops onto this. So a push, I call the work push method, and the pop I call the work pop method. And those work push or pops are here. Push is, whoops. Push just basically says, does it fit? Does it fit on the stack? Like if the stack doesn't exist, or if it's too big, then no, it's not on the stack. Otherwise, I check to see how much space is on the stack, and it's literally just a push. Does it fit? And if so, it's going on the stack. If it's going on the stack, there's my malloc, if you will. That's just a push. Take the current stack pointer. Actually, it's working from top down. Increment. And oh, increment for here's this is static, and this is my top pointer, if you will. So it's initially 0. P work is 0. And then that's my result. And then increment the pointer into the work stack. So this is the top of the stack that's being incremented. So the stack is moving downward. And then that's my malloc, really fast malloc, if you will. Otherwise, malloc, call my malloc method. And so this looks like a lot of extra work, but it allows me to avoid lots of little tiny little bitty mallocs like this. It's like this thing down below is going to be equal to probably the number of tasks. I forget what it is. It's going to be there 3 times the number of tasks plus 1. Well, that's going to be like, if I have 16 cores, I might have 100 tasks. This is 300 words of memory. 2.4 kbytes. I'll just stick it on the stack. It's so small. Now, if I was doing this with sane compilers, of which all but one is sane, all I would do here, this is ridiculous. It's like, come on. And this is what I had before. I would just say the following. I would just replace this. This is fine. Just work 3 times n tasks plus 1. There, full stop. What's this object and push pop? That's ridiculous, right? Just use a variable length array in C. It's fine. It'll be fine. You put it on the stack. Nobody will notice. The compiler will just say, here, sure, go for it. Microsoft says, what is that? It doesn't support it. The Microsoft CL compiler. It's a piece of garbage, but a lot of people use it. Nuts. Okay, fine. I'll do it myself. So I'm doing it myself. So this is Microsoft friendly. This is the Microsoft stupidity thing that I had to put this in for, these work push pops. Because that's what I had before. Before I ported it to Windows, everything worked fine with these variable length arrays. until I hit the Windows compiler. And I had issues with two things. This small workspace stuff, like size, number of tasks, number of threads, trivial things. I don't put anything order n on the stack anyway, that's too big. But little things, why not? Right? Nobody's going to notice 32 bytes, 32 words, 100 words, 2.4 kilobytes on the stack. No one should care. It should just all work. Until Windows. The other place where this is a problem, this G, I would really like to put it on the stack, but I can't, is scalar user-defined data types, or just scalars in general of the data type in question. Okay. Because those could be technically of any size. 8 bytes, they could be 100 bytes, they could be 1,000 bytes. But it's just a scalar. Oh, just stick it on the stack. Use a VLA. Oh, whoops. Windows says, sorry, I don't understand that. Okay, so fine. So this is my, I do it on the stack anyway, because it was all over my code. There's just too many places where I say, look, I just want a void, GB void is just a uint8. You can just do arithmetic on it. Like here's my scalar. Here's a scalar for beta. Here's a C scalar. And it's the size of that data type. There's a little macro hiding there called GBVLA. In sane compilers, GBVLA is let's see, where do I find it? Sorry, we're getting really deep here on some of these. Here we go. In all but one compiler, GBVLA, VLA for variable length array, is just it, right? If you've got VLA in the compiler, then VLA of S is just S, because it's a standard C variable length array of 8 bytes or 1,000 bytes. If you have a large user-defined type of 1,000 bytes, that's a big type. That'll be fine. And Microsoft Windows says, no, I don't know what the heck that is. Okay, so in Windows, using the CL compiler only, Windows GCC, Windows Clang, no problem. Windows Intel compiler, no problem. Just Windows CL. It doesn't tolerate it. So though all those arrays just become 1024 bytes. I don't use this work thing because it was just too messy to do. It appeared in too many places. So it's just 1 KB for a scalar. What that means is that when you're on Windows, and it's actually right here, if you're on Windows, and this is the user, this is the type new method, GXB type new, but GRB type new calls this method. And I come down here, and if I say, where's the size of type? Let's see. Yeah, here we go. I've now determined the size of the type. I'm about to return this great new type to the user. Oh, but wait, is it too big? Well, who cares how big it is? I mean, if you could declare a user-defined type of 3 megabytes, good luck, right? I mean, that's kind of crazy. But if it fits on the stack, more power to you. Well, if you're in Microsoft Visual Studio, I have a limit of 1024 to any user-defined type. So you can't declare a user-defined type bigger than a kilobyte on Windows. I return, I say it's too big, go away. Because the rest of my codes assume it's no bigger than 1024. GLB VLA size. And if you want it bigger, then fine, just redefine the macro, make it bigger. And everybody, the only one that will see it is Microsoft, because everybody else says they know how to handle that. So that's the other place where I use variable length arrays, which I still use in a good compiler, but then I don't use that on Windows. But over here, these were different, like number of threads, that is truly variable, and it could get large. So I thought, I'll put in my own stack. And that's what the workspace does. So that's a deep dive into the workspace. What else is in the workspace? That's about it. What is the status code? I forget what that is. Oh, this is for error handling, which is kind of then goes in the, it really probably should go in its own file, but this gets called here. When there is an error, it gets written to that logger handle, which is then a pointer back into the user's input matrix, right? Allocate that string, stick it in there to indicate, hey, there's an error that just occurred. So I thought I had, where is the error handling? Oh, let's see. Anyway, okay, so where am I? So that's the VAC space. So let's go back. So we left off with, and this deep dive here. We're in the EY's add. We're digging deep into this method. Okay, so now we're digging deep into add 0. All right, so I know that's a lot, but when you see this, when you see this again, well, this is used everywhere. So how many threads am I using? What's my workspace chunk? This will be used to determine the actual number of threads I want to use based on the max. And the chunk is, if I have, say, 20,000 units of work to do, whatever that is, it could be 20,000 entries of matrix to compute or something. And the chunk size is 64K, that's what it is by default. Then that says, well, just use one thread, it's too small. But if the work is, say, 128,000 and the chunk is 64,000, oh, use 2 threads and so forth. I think of you see the ratio until I reach the maximum, then I'll use all the threads. So I ratchet down the number of threads I'm going to use for every one of my parallel regions. There's always a num threads clause. So you can control that from the context. You can control that also from, I can then control this from this decision that says this for loop does not merit 8 threads, use 2 or use 1. All right, so now this is how big of a file it is, 800 lines. Okay, so get the content of the matrix, determine, is it hypersparse not? Here's this. Now here's another thing where it's 32-bit, 64-bit. This is AH declare, which is basically going back to this mdecal macro for the A matrix, which is just this. And in this, I wouldn't have to put this in here. I could just call it use the standard, use the mdecal for everything. However, whenever this is in a JIT kernel, this will be specialized for that particular matrix. See, this is the JIT case. If I'm in the JIT kernel, AH declare will be determined by the JIT kernel based on the number of bits for that particular component of the matrix. And that thing will be inside the JIT kernel will be a single pointer of the given type and the number of bits. So I can specialize it down just one pointer. And so to be consistent, I then, for every time I want to grab the H, the P, the I matrices, components of a vector, of a matrix, P, H, or I, or the hyperhash, I just use this declare macro throughout, usually. There's a few places where I don't, like here. It's just void. And the reason that's void is because I don't need all 3 pointers. I just need one. This method here will use the AP array, but it won't have to dereference it because it's going to just pass it to another method, and that method will dereference it, and that method has to have the 3 pointers. I compile my code right now with, especially going through this 32-bit, 64-bit edit, with pedantic warnings and with error set so that if I find a warning, it's turned into an error and I stop compiling. So I have a clean, very clean build as a result. There's no warnings that come out. And it'll warn against unused variables. This is declaring 3 pointers. If I don't use them, it'll say, hey, AH32 is unused. Well, it's using them, so it doesn't complain. Well, this is telling me it's actually useful because this is saying I don't need those 2 extra pointers. I'm just using the void star version of it for the A, the B, and the M matrices, all 3. Now I want to, okay, this is, you're going to see this in a lot of different places. And so now I've got to determine the number of integers, the sizes of the integers used for the output matrix is the P, the J, and the I of the output matrix. So that's what's being determined here. And it's determined based on several considerations, several inputs. These are all the inputs to this method. What sparsity are you asking for? Well, this is auto. Auto means it's a placeholder here for just, is it sparse or hypersparse? I guess technically at the user level, it could be bitmap or full, and I choose automatically. But here, internally, I use it just for sparse or hypersparse. And so I have integers, that means I have integers to choose. If it's bitmap or full, then these are always just false, because there are no integers. I have to pass in the 3 sizes of the matrix: number of entries, and the dimensions, number of rows and number of columns. Well, I don't have number of rows and columns. I have the vector length and the number of vectors. That is n rows or n calls, depending on whether it's stored by row or by column. Okay, but I also have the vec, which has those little controls, P control, J control, I control, from the input matrix of this problem. And this then is using those rules. It's a very simple set of rules to decide how to build the output matrix. I won't belabor that, but that's there in the code. It's easy to understand the logic there. And then I'm going to tell the caller, what my decision is. And then I went to, later on, I'm going to have to use a few decisions. Later on, I'm going to have if I malloc something, how big to malloc it. And I have a type code for these 2 types. Later on, you'll see why I need that. This type code is my internal type code. I think it's also, there was a type code added to, let's see, that may be different, to the user interface, because there's a type enum at the user, but this predates that, so they differ. I forget how different they are. That would be actually useful to know. I think it's in GB opaque. Yeah, here's my type codes. Oh yeah, I think they actually specified type codes in the spec, and they didn't match the ones I already had. I remember. And so I just have 2 sets of codes, I think. Wait, what do I do? You went 32. Here we go. That's type. There's an enum somewhere in the spec. Yeah, there it is. And I think they specified these numbers. And they didn't match mine. So I made 2 sets of 2 enums. And I don't get them confused. They're easy to keep straight, but so be it. The user doesn't see these, and I don't see these except in very few places in the code, in my code anyway. So there are 2 type code enums, unfortunately. Had this been around from the beginning, I would have used it over here, but I didn't, and I didn't want to go change my code to update to the new ones. This is a recent addition to the spec, and this I had to do at the very beginning. I did this 10 years ago now, almost 2017, because I had to enumerate all my codes, all my types. Okay, I'm going to need this because as you'll see later on where these codes are used, because I'm going to have to do some typecasting in particular. Okay. So now I have to I'm computing the hyperlist of the output. Okay. First of all, if I'm using the mask and the mask is hypersparse and not complemented, then CH will be just MH. It's going to be will it be shallow? I forget. Just to make a pointer to make a copy. I make a deep copy. I think. Are any of these shallow? I think no, they're not shallow. So CH is computed as a it's not a pointer into another array, another GRB matrix, but in the E-wise mult it is. It's different. So CH is MH. It's just a bool that says I just made a deep copy of MH into CH. Okay, and so if I have a hypersparse mask and the mask is not complemented, then that's the list of vectors to compute for C. Simple. And so I allocate my mappings. There's a method up the top called allocate result. That's a static inline that says allocate my pieces. Allocate, the output CH and allocate the 3 mappings of C to M. These are the mappings of the vector IDs, the one vector to the other. And I may or may not choose to allocate them all. Like if I don't have mask, I won't allocate this. So here, if I don't need to allocate it because I don't need it. I have a mask, but CH is M. I don't need to allocate the mapping from C to M because C is M. Is identity mapping. And I don't need to allocate it if A is a sparse matrix. There's no mapping needed. I know right where to find a vector of A immediately, just by the index of C. Okay. This is an example now of saying, okay, now I've allocated this output. This is just a void array. I need its content, but it's two types. And so the iPointer macro gets me a pointer to an integer array, and it's just going to do this. It's going to set one of the two. CH32 gets set to the pointer CH, or CH64 gets set to that pointer, but not both at the same time. Now I need to make a copy, and I could have done this as I could still change this, but I made a mem copy before, but now it's not a mem copy. Now it's potentially a typecast of an integer array from one to the other. So I have a method called in the cast function called gbcastInt. This is new. This is a mem copy or a cast between 32 or 64-bit integer types. And so I pass in my own internal type code for the destination and the source and the number of integers to compute to use and the number of threads to use. And then I just do either, if they match, it's a mem copy. Well, that's technically not a match, but it's close enough. You can just do a mem copy. And GB mem copy is my parallel mem copy. But if it's, say, int64 to int32, well, then my destinations, they're cast to the int32 and 64, and I pull in my cast factory. So cast, wait, what? Cast file. Oh, there we go. Edit cast factory. Naming conventions here. Every one of these source folders has, I think I've mentioned this, I forget. It has potentially 3 subfolders, one called include, one called template, one called factory. Factory is source code that is only used outside of a JIT kernel. Template is used inside a JIT kernel. It may also be used outside a JIT kernel, like in code like this. And then include is an include file that could be used anywhere. So
we
the
covered
cast
some of that in the JIT session.
So this is the factory. It's trivial. Just make a copy, parallel copy. But those 2 pointers could differ. I wouldn't have to make this a template. It's so trivial. I could include it literally right here, but it just felt better to do it this way because I have it so many different places. So this is doing typecasting or mem copying between int32, uint32, int64, and uint64. Those between those four cases. So there's like what, 16 different options of casting. And so that's what's happening here. Then I have to do a mapping now. I have to know, I have to do a set union of A and H. Well, I don't have to do a set union yet. This is not the set union because C is M. CH is M, MH. But I basically have to go through and look up for every vector in the output C, find the corresponding vector J. So J is the vector in C I want to find in A, if it's hypersparse. If it's not hypersparse, there's no work to do. And if I find it, put in this mapping. So I can know, oh, the kth vector of C is the kth vector of A. That's what this hyperhash lookup is doing. And I've described the hyperhash, I think. It's basically doing inverse search. It's looking for that Ka such that if it exists, if J exists in the A matrix, that's what it's that kth vector in the AH list. Makes sense? Otherwise, it's not found. And so I stick a -1 to say it's not there. And I do that with the easy to do, the add for that. There's nothing to do. It means that the A is empty in that location. And I do that for B as well. Okay. Otherwise, I have like 3 different cases to handle. 4 different cases. Okay. A and B are both hyper. Okay. Now I have to do a set union of the 2 hyperlists of A and B. I can't use order n time or space. N could be 2 to the 60. So in this case, I'm not using the mask. I think it's too expensive to use. I just want to find the set union of A and B. And so that's what this code does. And I call actually a parallel. I have a function called slice vector to it's slicing these 2 arrays into subarrays. I'm going to find the set union in parallel. Yeah, they could be big. And I don't know if you wanted me to go into detail of this method or not, but it's constructing a collection of tasks, which is returned. Where is it returned? In the workspace here. It says where does each task start and finish inside these 2 lists. And then every task to construct CH knows where to start in A, where to start in B. And then I can just do the set union. Because AH and BH are 2 sorted sets. I always keep the hyperlist sorted. So I'm doing a set union of these pieces, and it has to be done in 2 passes. The first pass just does a count. And you can see this I get again, because again, every time you see this I get, this means, well, there's actually 3 pointers. There's AH, AH32, and AH64, and this is accessing either the 32-bit version of the data or the 64. And of course, there's only one version of the data. One of the pointers null. And that's just, and so this first pass is just counting every, so then it keeps track of the count. This is doing, let's see, KC is 0, and it's, this is the offset for the end. Let's see, no, this is the number of entries I found, I guess, yeah. How far did I go in A and B for this task? This is just doing accounting for this task. And then I do a cumulative sum of the tasks, so every task knows where to start. And then I have to do this work again, but actually fill the CH array. Same logic here, but now every task knows where to put its result. And this is the putting of the result. So this line of code is this is the iset macro. In my, if we would have talked 2 months ago, or even just a month ago, you would see this line of code highlighted as the actual code, because it's all 64-bit. Now it's this. But since this is a little bit obscure, iset blah, 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 I'm always following the iset macro with an actual description as to what it's doing, because it is kind of a little bit, you know, macro programming can get overkill, can get overly. So it's doing this ternary. It's not a ternary, it's, you know, if and else. Okay. But it's kind of hard to read to know what it's doing. So conceptually, it's just doing that. But CH, of course, is void. Can't do that. I have to either write it to the 32-bit pointer, the pointer to the 32-bit space, or the pointer to the uint64 type, one or the other, which is what this is doing. So I'm loading in those things, and if it's not found, I have to put a -1 in there to tell me it's not in A, but it's in B, and so forth, or it's in both, and so forth. So this is computing the set union of AH and BH, but it's also computing the mapping. That's what CH is. This is set union, but it's also computing the mapping. Where do I find a given column of C? Where do I find it in A, and where do I find it in B? So that when I go back over and do the actual add, I can just quickly look up. I don't have to do this hunting and searching business. Like, I don't want to do a ton of hypersparse lookups all over again. These are expensive. Here, I figure I might as well do it, because typically I'm only going to do this with a very sparse mask anyway. So AH and BH can be really big, and the mask is tiny in this instance. So a lookup by potentially a binary search, or if there's no hyperhash, or a lookup into the hash table, which is, you know, order 1 time in practice, you know, is reasonable. But here I'm not using the hyperhash. Okay, then and this is all this is all debug code. You see this right here? It's like this was a somewhat subtle algorithm here. I mean, do the counting, do a cumulative sum, go back over it, figure out, right? It's a parallel set union. It's like, really? Yeah, it's kind of, did it work? Well, let's see. If def gvdebug, rerun the whole algorithm with 1 thread and make sure I get the right result. And the 1 thread algorithm is really simple. And so this code is serving 2 purposes. One, it's nice for debug, because if I fail, if I compute something wrong, oh, well, this code will tell me. And 2, it's actually useful for me when I look back at the code. It's like, what the heck? What is this slice vector thing doing? And, well, you know, what is this cum sum and counting and blah, 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 blah. Oh my gosh, this looks complicated. This is all it's doing. It's just doing a union of 2 sorted sets. Oh, look. Oh, start at the beginning. Iterate while both A and B have entries. Get the entry. If A appears before B, it's in A but not B. If it's in, you notice here, these are now just assertions. Oh, it's in both. Oh, that's handy. Oh, now you're done with this loop. You're out of the loop, which means you've got either A or B to clean up. So there's the B is exhausted, A is not, A, and so forth. And we're done. And you've found all the vectors in C. Oh, that's easy to understand. It's a single threaded set union. Cool. Oh, this is debug code, but you know, it's handy. I consider this essential part of my software. Okay, now if this is simpler case, if A is hyper, B is not hyper, then there's just the one mapping to go is really simple. The mapping is simple. Basically, I have to go through, there's no hyperhash lookup. I just do set it all, oh, it's not there in the C matrix. Because now C will be sparse, not hypersparse. So there is no CH array. And this array is of size n. It starts as -1, and I just need to scatter the hyperlist of A into this mapping C to A. So I'll know where to find it. So this is like a quickie inverse of the A. I could use the hyperhash, but I don't need to, because I have size n space for other things. I might as well use it here. So it's really simple. And so same thing for the opposite. If A is not hyper, B is hyper, and so on. And if they're both not hyperspace, it's super simple. There's no work to do, except to allocate potentially a mapping of C to the M matrix, which is potentially hypersparse. But this is the decision, making this decision when C is not, H is not MH. That was made up earlier. Now, finally, if I need the mapping of C to M, it only happens, this is a really, useful thing to remember. Oh yeah, this is only the hypersparse case for M. And then I need to look up, so I do all the hyperhash lookups and I stick it in the C to M matrix. So it's like an expansion of that hypersparse lookup. So then I don't have to do this once, and I don't have to do this multiple times later on. And if it's sparse, it's the easy case. So that's it. So I'm all in this first phase then, and then finally, I'm at the end of the code, I'm done, right? Well, no, I'm not done because I want to check it. And this is what this algorithm has just computed from here to the bottom. And in parallel, this is a single threaded code. So what is this computed? Well, first of all, I'm not even anywhere near this algorithm if C was bitmap or full. And so this says, oh, I'm walking through all the vectors of C. If it's the kth vector, if C is sparse, it's down, then it's here. This is a Cn vec is just n, number of columns, say, of the C matrix. And C will be sparse, and J and K are the same. The kth vector in the output has the name J. There is no CH lookup. Otherwise, it's this. Okay, so this is in the data structure already. There's no work. This is already true on input. But I can now iterate through, and now I know that, oh, if there's a mapping from C to A, this is what it tells me that mapping gives for me. It says that, first of all, A must be hyper. If this exists, A must be hyper. I can look up in this array, and I know that that is the vector I'm looking for. That's the vector J I'm computing for C. This mapping is an inverse of this, basically. You see, this is going K equals C to A of K. This is going the opposite direction. I don't get K, I get JA. Well, actually, where J is J itself. It's a different kind of mapping in the hyper, but it's an inverse of the hyper. That's not just an inverse, it's a mapping of the kth vector of C is what vector of A. Otherwise, I don't have it because A is not hypersparse. And the same thing, mapping is for B. And then if CH is MH, I just made a copy of it. Otherwise, I have a mapping to it. So this is describing what I've just computed. And this is really common for many of my algorithms. I'll end up with, this is 100 lines of code just describing what I did, but it's in executable code. So I can know that, I know that if I turn on debugging, this will work. If I make a mistake, I know I can kind of figure out what happens. And that's it. That's phase 0. That's 240, phase 0 of one method. Yeah, this is not easy code. Okay, so, I'm not here yet. I have to go to EY's slice now. This is our first major algorithm, EY's add. I mean, the others have been, a lot to them, but there's a lot to these add, multiply, union, EY's mult, things. Those things, assign, those things get complicated. Okay, so that's phase 0. Now, if the matrix is sparse or hypersparse, I do the slice. Okay, so the slice is in the EY's folder, back to here. Oh, wait, no, it's not, sorry. It's in the slice folder. The slice folder is a folder where Yeah, all of the methods, most of the methods I have for chopping up matrices into pieces to compute in parallel. Slice. Okay. EY slice. You notice it's tagged as executable only because that just tells me, oh, it's got a fix me in it. That'll be gone by the time I release the code. Okay, that's just sort of, it colors it red so I can remember. All right, this slices entries and vectors of two, yeah, of a bunch of matrices. So it's gonna compute this, gonna compute some tasks. Now, this task list is not just a handful of integers anymore. It's its own struct. So this is a bigger thing. I use this in several places. It's an array of structs. Or is it a struct of arrays? I forget. I think it's an array of structs. Yeah, it's an array of structs. And that's what EY slice is computing. It's deciding, it's computing this array of structs. How big is that array? In GraphBLAS, SuiteSparse GraphBLAS, every single pointer I get from malloc, I keep track of the size of the thing I just malloced consistently. And that's really useful for several things, for asserting that when I free it, it's the size I say it is. And then my memory manager will tell me, hey, wait, there's a mismatch here. That's a nice way of finding bugs. And the other useful thing is if I want to reuse the memory space for something else, oh, it's big enough, great. How do you know that if it's just a pointer to malloc some space? Like, how big is it? You can't ask malloc how big it is. Well, you can ask me. I know, I kept track. And the other useful thing it is, which the thing that's useful for all of these, and this is true even in any data structure. So if you look at, say, the built-in the contents of a GB matrix, which I've renamed GB matrix content now. It used to be called just GB matrix.h, but that was not general, and it was too general. Every pointer, username size, logger, char star, it's malloc. So there's a size of the malloc block. The header size is the size of this struct that contains this data. All of these pointers, the P, the H, the I, the X, the B, they have a size, number of bytes that were malloced. Here, this thing, it doesn't, this is an array of structs, so I have to keep it separate. And then it's also going to determine how many threads am I going to use and how many tasks those threads will do in the rest of the parallel phases, phase 1, phase 2. Okay. These are just inputs. I just computed those in phase 1 or phase 0, sorry. And this is the input from the user, except that I don't pass in a mask if I decided not to apply it. Otherwise, I pass in the 2 input matrices, the 3 input matrices, A and B and M. And everybody gets the vark because, lots of people need the vark. And usually it's the last argument of all my methods. Okay, EY slice. What I'm going to be doing here, let's see if I remember correctly which slicing this is going to do. Yeah, it's long. Okay, right, I remember now. Okay, yeah. All right, so this is a kind of parallelism that is going to be done with potentially three input matrices. And it's going to be done with a complex set of tasks descriptors. And it's going to be given the mappings from the output matrix to the 3 input matrices. And this is used for EY's add, EY's multiply. It's used for some of the assign methods. And I forget which others I showed you at the beginning. Okay. I think I already explained the EK slice method, didn't I? Of how I slice up a single matrix for parallel computation. Didn't I do that? already? I think I did. You've probably seen that before.
Yeah.
Yeah, I'll just draw a picture just as a way of reminder. Suppose I want to chop a matrix up into 3 pieces. Oh, I've got the fuzziness. I'm going to turn on turn off my blur. There we go. Okay. So this is what EK slice is doing. If the matrix is stored by column, if I had chop it into 3 pieces, it may chop some columns in half. Because what I do is I take the entries, of which are E of them, and just divide them into 3 pieces. And then I figure, oh, I landed in the middle of a vector. Right? That's like, oh, no problem. I'll just cut the vector in half. And the nice thing about this method is that if I have a very sparse matrix that's got a stinking dense column in it, I may use 1 or 2 tasks to compute the first half of the matrix, but then I may cut this up so much that, you know, I might come along and say, oh, look, this vector is so dense, it's going to get lots of tasks in it. Because I took a million entries and divided into 16 pieces. Oh, look, you're in the all these tasks are just in the middle of a vector. Yeah, that's a nice way to parallelize it. It makes sure I balance the work. I can't just say, oh, just balance the vectors. Well, what if you've got a million entries in your matrix, but they're all but 10 of them are in one vector? You get no work balance. You get one thread working, doing all the work. So that's not very good. That's the EK slice method. I call it EK because I cut the entries E, and then I find the Ks that they are in. That's why I call it EK slice. I don't know. That's just the name that came to me. I don't have to come up with names that mean anything to anybody else. They just remind me what I'm doing because I'm writing the code. But of course, if you're looking at the code, that's something altogether different. All right. So, but this method is not so simple because I have like 3 or 4 matrices to chop up into pieces to know, oh, you do this with the C matrix, and this is the A matrix, and this is the M matrix, this is the B, and ooh, you know, it's a little more complicated. So here, I have to do something slightly different. I may do something like this. I might decide, oh, look, here's a pile of vectors in the matrix. I call this a coarse task. It's going to do multiple vectors of the input matrices, output matrix. And all of them are sparse enough, group them together, do it as one task. Oh, but this vector has got a ton of entries in it. Split it individually into some subtasks, which I call fine tasks. There's coarse and there's fine. So these are fine tasks. And they're going to chop in they're going to slice individual vectors of the input or output matrices into pieces, which you've already seen the method. I haven't dug into it, but I would call it slice vector. GB slice vector is going to do that for me for one vector. It's going to divide up the work because, oh, there's a million entries in one vector, one dense column of a matrix, say. That's bad for parallelism. So chop it up into pieces. Or maybe this EY's add is being called, there could just be one vector. Because I use this for GRB vector add as well. Right. This is not just GRB matrix add, this is add. This is being called, look, I mean, if I go to GRB vector add, it calls the same path. And I just say, you got a vector? Nah, it's a matrix. I just cast it. It's just an n by 1 matrix. So there's only one vector. I can't just say, oh, spread the vectors out to all, well, it's just one vector. I got to chop it up into pieces. That's only going to be fine tasks. Okay, so this is the job of EY slice. It's a different slicing than this. This is easy to do, but it only really works nicely if I have one matrix to deal with. If I have lots of matrices to deal with, I have to make it cohere. I have to do the slicing that's coherent across all of the different matrices. So if I come across a column that's really dense in A and very sparse in B, well, or very dense in C, I'll slice A and B and M and C, whatever, the same consistently for that particular vector of the matrix. So this is something I can do in a consistent way, is the word I'm looking for, across those 4 matrices. And that's what this method does. And so now, because I have to do binary searches, I don't tolerate jumbledness. And I'm going to create what's called a task list. So what's that struct look like? There's the mdecal. You know what this is doing now, because now you can say, oh, that's going to be 32-bit, 64-bit. Yep. And there's a Verk space, and I mentioned here, oh, it's going to be small. Okay, so allocate this workspace. This is a struct. Let's see, where do I put this struct? I don't remember. It's probably in my slice. It's probably in here. I don't remember where I did the here it is. Oh, include task struct. There you go. Of course. All right, there it is. And I'm going to declare an array of these, 1 per task. And so it's going to define one or several things. The course task is easy. Okay, first. Okay, last. Like, oh, take the vectors k first to k last and do that. Okay. Course tasks is easy. A find task, I have potentially up to 4 different matrices that have to cut apart, but I have to cut them in a consistent way. Like if I have a task that's going to work on, say, the first part of this vector, and it has to have the same, so it's potentially a very long, very, very big vector, lots of entries. You say this vector is going to work on rows 0 through 1,000, say. Well, where are those in the C matrix? Where are those in the A matrix? Where are those in the mask? Where are those in the M matrix? And they're all different sizes in different places. But you see, this will tell me where they are in those potentially 4 matrices. Now, some of the usage of this task struct, these will be unused. Sometimes I'll just use 2 of these if I have 2 matrices to deal with. So these names will be I mean, I don't know, I could have done this in a more, anyway, that's how I did it. And so because I reuse a struct for many different, slightly different kinds of slicing of work. But this is the single data structure called the task list. And I have a method called, I have a macro, a file called task methods. And I have a macro called realloc task work, which you're seeing right here used, which says, and right now I have no tasks, it's empty. So this is going to allocate the space and set it to empty. But it can also reallocate it if it's too small. And so as I'm working, what's going to happen is I may do some initial cutting of these matrices and decide, oh, wait a minute. This course task is too much work is put into this course task, and it's only doing a single vector. Oh, I got to slice it into find tasks. How many find tasks? Well, see, all these decisions I don't know until I actually go cut up the work. And so I don't know up front, unfortunately. If I was smart enough, maybe I could figure it out, how many tasks I'm going to end up creating. So I use the realloc for this. It starts out empty as null. So the first thing is a realloc of a null pointer, which allocates some space. And this is just an estimate. if the estimate, first of all, if I'm only using one thread and no mask, this is single task, we're done. Otherwise, it's 32 times the number of threads. So if 8 threads, you know, what is 8 times 32? Whatever. 32 threads will be 1,000 tasks at most, I hope. But it might grow beyond that. Whoops. And then I reallocate. So this can do the realloc. And then I try to like double at best, I try to at least double it in size. I think that's what I do here when I double it. Yeah. The new space is the old space times 2. So it's the doubling approach to dynamic storage. So I mean, it's could be cleaner, but it works well. All right. So again, so where are we? We're in the EY slice method. So this EY slice method its job is to do this for up to 4 different matrices in a coherent way. And so let's see. Yeah, there's no other things it calls. It's always, well, it's self-contained except for this method, which I'll probably dive into. You saw it before when I was cutting the hyperlist. It's a similar thing of cutting a single vector. It's 2 sorted lists, cut them up into parallel work. Did I edit something? No. Okay, good. All right. So declare my arrays. And so you see what this is doing then. This is declaring 3 arrays, the 3 pointers. Void, uint32. Actually, sorry. Yeah, uint32 and uint64 for that component. And the same for B, P. And now the hyperlists I don't need except for debugging. Because I don't know, I guess I don't need it. But I need the MP array. And now I also get the content of them. So I get the content of the 3 input matrices. The output matrix is just CH. It's not a matrix yet. There's no output matrix yet here. The input is just the mapping and potentially the hyperlist of the output matrix. There is no output matrix yet for this method here, UI slice. But I do have the 3 input matrices, 2 or 3. Because I think, yeah, A and B are always present. You can see here, it says matrix okay. This is saying the matrix is either okay or it's a null pointer. Because there might not be a mask at all. Okay, so I need some workspace. This workspace got pretty big, so I didn't put it on the Vark stack. I just malloc it. Let's see. I make a decision to use smaller integers though with this workspace. This was something I didn't do for the C to A and B mappings. I guess it's 3 o'clock. Maybe I should finish this method and we'll take a pause.
Yeah, and so
Yeah.
but I'd say we're probably about kind of halfway through EAD, right? We got to this from EAD.
Probably.
Okay.
There's a lot more
let's go ahead and stop
algorithms.
after
After
we'll stop
finish this
after
algorithm.
function.
Yeah. Okay. So I basically have to first, it's a multi-phase method. I first have to estimate the work to compute each vector. And this is an order cnvec loop. I get the name of the vector, which this is a macro, gbh of c. This is a 32, 64-bit thing. Where it's the hypersparse lookup. So I have a macro that does that because it could be 32-bit, it could be 64-bit, it could be null because it might not be hypersparse. If it's null, J is equal to K. If it's 32-bit and so it's present, it's AH of 32 of K. Otherwise, it's CH of 64 of K, and so on. So this is a 3-way test. So anyway, then I have to go and get, well, I've already found the mapping. I know where to find the A vector. I get the A vector, I get the, then I get the B vector. If I need the mapping, I get it. Or otherwise, if CH is equal to BH, which might be true, it isn't true for the add, I think. Maybe it is, I forget. And oh, it's not true for EY's add. This is the case where CH could be a shallow copy of, it just actually is literally a pointer to BH, shallow, not its own array. So I look up those three, and the estimate of the work is just add the two number of non-zeros in those two vectors. That's the number of work. And then I do a cum sum on the work, and now I have a total work for the whole C matrix. Very quick test, very simple work estimate, and find out how many threads I'm going to use based on that, and then slice it coarsely. So P slice, I think, did we see this method before? I think it might have been the EK slice. I forget. No, it wasn't. I don't think it was. Wait, was it?
I don't think we've seen it.
Wait a minute. ACK GDP slice. No, we haven't. Okay. Okay. Okay, so P slice, it's super simple. If it's just slicing up either bunch of entries uniformly, which is just literally partition the space into tasks, or I call a 32-bit or 64-bit variant, depending on the type of C work, which is in the template or the factory. It's in the factory. There we go. Okay, it's very simple. Well, no, it's not simple. Actually, it's pretty elaborate. Okay. Oof. All right. It's recursive partitioning of some work. Okay. All right. Partition some work into a set of tasks. You see, but the work is irregular. This is an array of size nvec. C work is. It's the number of work every column needs, and it's been cum summed. So imagine a function going from 0 to n, if n is the dimension of the C matrix, and that work, that cum sum, is going to go up and up and up and up like that. And if I have to create just two tasks, I want to do a binary search for work over 2 to find out, oh, you get 80% of the vectors because 80% of the vectors have half the data, and the other 20% have half the data. So I want to do a binary search on the cum sum to look for work over 2, and that tells me where to slice. And that's basically what this is doing, but it's going to go more than that. And so what I do here then, there's two kinds of balancing, and here I don't care if it's perfectly balanced because it's just EY's add, and it doesn't need a perfect balance to be nicely balanced work. So what I do is I've got some number of tasks to create. I've already chosen that, and that's this number here. Then a quick test if, oh, there's only one amount of work to do. Everything is in this one slice. Okay, otherwise, because this is actually a recursive algorithm, I start by saying I don't know where to slice anything. But I do know that the slice of 0 is 0 and slice of n tasks is n, which is a pointer past the last unit of work. Now, where do I put like the 80-20? If it's just two tasks, there's a slice of 1. So this, if n tasks were 2, this is slice of 0 is n, slice of 2 is 0, sorry, and slice of 2 is n. Slice is a size 3 if there's 2 tasks. Slice of 1 is not yet defined, but that would be that 80-20 split if 80% of the vectors have half the data, half the work, sorry, because this is a work thing I'm slicing. The input thing is called work, whatever work it is. In 64, U in 64, it depends. This is templatized. Okay, Ignore this perfect balance because they're going to do some binary searches and they don't need to if most of the time. So most of the time it's enough just to do the simple case. So here's this is the non-parallel, this is the non-recursive method. It calls the recursive worker to say, slice up all the work. So what does the worker do? The worker is up here. And this worker is going to call itself recursively in two pieces. Okay. What it's going to do, it's got a sub region of the data of the slicing to compute. Okay. And from low to high, it's being told to say, okay, slice the work into low to high. And and I already know where the boundaries of the work is. It's at these are already defined on input, the low and the high, like the 0 and the n, the very beginning. Okay, so find out where those 2 points are in the work. And if there's nothing to do, just all empty in the middle. Otherwise, suppose I want to cut it. Now this won't be a very good balance. I say, well, what if I got 2 tasks to create in this space? Okay, what I do is that, well, fine, I'll just cut the whole thing in half. And then where am I? So this is an approximate balancing. So I just cut the thing in half. That's probably not a good choice for just 2 tasks. But just cut the thing. And then if I've got more than 2 tasks, this will be fairly balanced. Because what if I cut it at the 80-20 and maybe I want to create 5 tasks? I cut it in half. And I look at this and say, oh, well, just put 1 task in the first half. And that's what this, let's see, n tasks, T low. Let's see, wait, what is T low and T high? T low and T high are the inputs. Yeah, this is the number of tasks from like task 5 to task 92. You're trying to choose what those tasks in the middle are wanting to do. So what I do is I slice the work in half, I think. I slice the region in half of the work vector. And then I say, well, oh, look, the cube sum is here. So what if it's 80 and 20? I'll say, fine, I will put, depending on where I cut it, I'll say, ooh, most of the work is to the left. So assign say 4 tasks to the left and 1 task to the right, perhaps. So that's what this will be doing. It's choosing which task from say I have 6 tasks to put in there. So, oh, I cut it the work in half. I cut the space of the work in half. I'm not doing a binary search, just cut it cheaply in half. And then I look at how much work there is on either side of that halfway point. And if the bulk of the work is onto the left, I'll put most of the tasks over there and just maybe a fewer tasks over to the right. And then I'll just repeat recursively. So it's a very cheap cutting of the work. And it could end up with slightly imbalanced tasks. But it's really fast because you're constructing all these tasks all at once. One dive into so it's like, the time is like order T log T if you have T tasks or something like that. It's super fast. And just recursive repetition based upon, oh, I've got this 4 tasks to do this and say 2 tasks to do this region. So I'll cut it in half and then choose how many tasks go in which half and cut this in half. And if it cuts evenly, it's 2 and 2. So I have 4 tasks, cut it in half. Oh, that's a good place. I'll put 2 here, 2 there. That's good enough. But if it's very imbalanced, I'm going to put 1 and 3. And so forth. And then, 3, I've got to dive deeper for that. Keep going. So it ends up being a very clean little piece of code. It's very simple once you see it in terms of like lines of code. It's a little subtle, but it's pretty handy. It's really fast. However, that's just this method. All right. If I want a really truly balanced piece of work, then I do a binary search for each task. But now I'm doing, if I have T tasks to compute, the work is higher because I have to do T binary searches. Like every task will independently find where it wants to go. And I have to do a search of that cum sum. Okay, well, searching that cum sum then is a binary search of n data, not t. T is number of tasks is small. So t log t is way faster than t log n. N could be a billion, right? So t log n could be, oh, it's not so big, but it is a little, the binary search is a little slower than this. This does a lot more hunting and pecking than this method. And if I have, and what have I done here? Look, I've got number of tasks is 32 times the number of threads I've chosen for this particular algorithm for EY slice. So, that's fine. If I've got 8 threads, I've got a lot of tasks. And if some are imbalanced, I'm going to schedule them later on dynamically anyway. And that'll all even out. So it works fine. And it means that the slicing is quicker. So there's those two different methods, basically. If I'm allowing a perfect balance, if so, use this or not. Okay, and so that's pslice. This pslice method actually works with 3 data types for that work vector, that cum sum of the work. UN32, UN64, or float. Right? It's so approximate. Just use float and cut it that way. The only downside to using float is that, and most of the time I don't need perfect balancing, is that if it's float, I don't enable this option because this option, I'm looking for a specific item from the work vector of type integer, and I search for that, and that's where I cut. That seemed a little awkward to do a binary search on a float array, so I said I could get it to work, but I don't need it. And so when it's float, I only need the rough balance anyway. So I didn't bother to get this to work when the work type is float. So I just disable it. So that's pslice. So what this is doing here, it's cutting up the C matrix. Because remember now, I now have, for every vector of the output, I have the amount of work it takes to do all those pieces. And if you do the cum sum, you would see this go up and up. And then if this is a dense vector, the work would go up really fast right there. Okay, what the pslice has done for me now is it's given me a collection of coarse tasks, like say this, because I've just divvied up the vectors into coarse tasks. If it's a very, very dense task, it'll maybe just have one task that's doing one vector. It might be okay, but now let's check that. Okay, let's go back over the tasks and ask, okay, task, what are you doing from first to last of your vectors? Oh, we're done. Okay, skip it. Otherwise, oh, this is fine. You've got 2 vectors to work on, 2 or more. Course task, you're good. No need. Okay, oh, now we come to a course task. It's been given a single vector, or maybe no vectors, which is kind of weird, but it can happen. I have to remove it from the list of work because if it's 0, there's no work to do. I guess I just remove it. But I have more work to do because I might decide it's fine, right? I don't need to slice it up. No, this one I sliced up twice, right? But oh, I may need to replace this task. This course task is doing one vector. I might look at this and saying, hey, you're doing too much work. You need some help. Slice, 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 slice. And that's what I decide here. I go back over the vector that's just one now in the task, the course task. And this, you'll see this in the Saxby, like the matrix multiply, you'll see this kind of parallelism. All of this is just deciding what parallelism to use. If I had no parallelism, this code would just all go away. But I have to get, I'm in the K vector, I'm in this vector of C. Where am I in the A matrix? Where am I in the B matrix? And where am I in the M matrix? Again, all this is constant time, so it's very fast. It just looks complicated. How much work am I doing? Chop it up into pieces. And then, oh, I only need one piece anyway. Leave it. Just make it a course task. Put it back in the list of tasks, make it course. And then, oh, wait, I need some help here. So I need 4 tasks, 4 fine grained tasks. So I take this course task that's doing one vector, and I go chop, 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 chop. And that chop, 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 chop is, I've already decided how many fine tasks to do. So now I have to chop up those fine tasks. And this is a little expensive. I have to do the slicing for every fine task, this slice vector. Now, I guess in principle, I could do some of this in parallel. On the CUDA code, we do. We compute the tasking, we compute the parallelism in parallel itself. This is single-threaded. The slice vector algorithm, which we won't dive into today, it's too much because it's already 320, is going to cut the 4 matrices up, or I guess 3, into pieces, one piece. And the piece is the target work. Cut it here, please. Cut it so that if I do M of A plus B, mask of an A plus B on this vector, I roughly get this amount of work. And then cut it there, cut it there, cut it there, cut it there. And then that's what this fine task then does. So that's a mouthful. Lots of moving parts here. But this does, and we'll stop here, but this is the EK slice idea of cutting up work on a single matrix. Works great for one matrix, but it doesn't work well when there's multiple matrices involved to cut in parallel, like A plus B, a Kronecker. I forget what I do. I don't think I use it for Kronecker. No, I don't. But this I have to use for several methods, several of the EY's methods. EY's add, EY's multiply, EY's union, and also assign. Some of the assign methods look like an add or look like an emult, EY's mult, and those methods need this one as well. So, so that's why you'll see EY's slice called multiple places. In the add, in one of the assign methods, emult, and in the mask method, actually. And actually, many of the assign methods, I think I have this, it's hidden inside a macro here. Whoops. I think it's in many of the, I think it's called the 2 slice. Yeah, I use this in 1, 2, 3, 4, 5, 6, 7, 8 of my assign methods. I have to slice 2 matrices. And that's using the EY slice method as well. So it's like 1, 2, 3, 4, 5, 6, 7, 8 assign methods here. 9, this calls it directly. The EY's add, EY's mult, and masker. So what does that total up to? 9 of 10, 12. Lots of algorithms need this slicing method. Okay, so I think this is a good place to stop because
Yeah, I feel like we
described,
could almost do a whole session on tasking and parallelism. Yeah.
It's yeah, it was a big effort to get all these methods
For sure.
working. Yeah, and you haven't even seen, the matrix multiply is even trickier than this. It uses some of the same tasks. It uses the same task struct, but it builds the tasks in a totally different way.
All right. Yeah, we'll go ahead and stop recording here.